In this lesson, we shall focus on Math 142, a UKZN Center of Gravity and Centroid module. And obviously, a lot of concepts that relate to mechanics will also be done. We are getting started right now, just looking at the basic information and also some exercises that we shall discuss together. Let's get started. Right, first things first, we shall actually look at the chapter objectives. What are the objectives of this chapter? Right, the concept of the center of gravity, the center of mass, and the centroid. Next, we shall also determine the location of the center of gravity and centroid for a system of discrete particles and a body of arbitrary shape. We shall look at the theorems the theorems of Pappus and Gouldenus. Method for finding the resultant of a general distributed loading. So these are the actual chapter objectives that we need to focus on. And it is very, very important that we make the most of our time moving forward in learning and mastering this particular section. Right, so these are the objectives, but you take note of the fact that this lesson is recorded for control and quality purposes, and therefore you will receive the recording of this discussion at the end of this discussion. Okay, so you might not be able to always like write everything, but now what are the keywords here? The keywords are the specific concepts of interest as chapter objectives, which are the center of gravity, the center of mass, and the centroid. So these are the most important concepts that you need to learn. We shall as well solve tons of questions. So yeah, we're getting started. So if you do not copy anything, you don't copy everything, and you can just obviously see. There's some things you will write down, but in the end, you will have the recording for the 2 hours that we shall spend together. Right, there's a chapter outline. That is very important. Now, what is the chapter outline for this section? Right, now the center of gravity and center of mass for a system of particles. So we're interested in, most importantly, the center of gravity, but together with the center of mass for a system of particles. We shall also look at what we call composite bodies. We shall look at the theorems of Pappus and Gouldenus as well. And these will be the kinds of theorems that will be central in the study we shall undergo together. Next. The notion of the center of gravity and center of mass for a system of particles. Center of gravity and center of mass for a system of particles. Right, let's speak about a little bit about the center of gravity for a system of particles. Right now, looking at the fact that at this point, the center of gravity, first point, what does it do? It locates the resultant weight of a system of particles. Now, one focuses on a system of particles that constitutes a body, an object. And we attempt, therefore, to locate the resultant weight of a system of particles. And to actually, therefore, find the resultant weight, it is actually what then brings about what we call the center of gravity. So the center of gravity locates the resultant weight of a system of particles. Number two, right, so if we speak about the center of gravity, we need to consider a system of n particles fixed within a region of space. Okay, so we consider a system of n particles fixed within a region of space. So we take a sample of n particles, which are part of an entire region or an entire object, and we then say, Okay, we consider the system of n particles fixed within a region of space. Take a sample and then say, okay, we'll take a region, which is a system of n particles fixed within a regional space. Next, the weights of the particles can be replaced by a single equivalent resultant weight, having defined point G of application. Now, this is extremely important. So we are saying the weight of the particles, because each particle has its own individual weight. And so we're saying the weight of the particles can be replaced by a single equivalent resultant weight, having defined point G of application. Right, so this therefore becomes so much of interest. In other words, if you look at the first diagram, the diagram A, we really can be in a position to say we can be able to replace the weights of the particles can be replaced by a single equivalent resultant weight, having defined point G of application. Now, you take a simple particle there. If you take a simple particle, you are able to therefore find parallel distances. Now, the sort of distance parallel to the y-axis is called y tilde. The x distance parallel to the x-axis is x tilde. And similarly for the z-axis, which is the perpendicular axis, the small, this is like dw, sort of the small weight of this particle is obviously, we understand it to be a weight that's downwards by definition of weight. And also now, if you are to look at the fact that we can therefore, this is just a sample particle, because the weight of the particles can be replaced by a single equivalent resultant weight, having defined point G. So here's a particle that has some small weight, that's why it's called dW, but it can be replaced by a single equivalent resultant weight, having defined point G of application. Here's the point G right now, and we're thinking, okay, there are too many particles there, but we can just replace it by just one weight. One weight. Now, this weight has a defined point G of application. This point G of application is actually of great interest to us, the center of gravity. The center of gravity. Okay, so we shall determine this center. This section is devoted to that, to say what is the center of gravity. But now we then say, okay, we studied too many particles, but the weights of the particles can be replaced by a single equivalent resultant weight, having defined point G of application. And the point G of application is actually, now note a couple of things. We use here y tilde. We use here like y tilde. Right, we use here like y tilde, which is parallel to the y-axis for this one. This is the x-axis. I know it's a bit tiny, this, and this is the z-axis. Right, so now this is the x-axis. So parallel to the x-axis is x tilde. Now this one is y bar, and this is x bar, like this. So y bar and x bar are different from x tilde and y tilde. So x tilde and y tilde are sort of the parallel, like x tilde is the distance parallel to the x-axis, and y tilde is parallel to the y-axis. But now these x tilde and y tilde are sort of the distances that help us determine the position of a particle. Right, so the weight of the particles can now be replaced by a single equivalent resultant weight. We say, okay, we have just one particle, we have taken a sample particle with a small weight dW. Okay, so we wrote it's dW in this here, where the W itself is a vector. Now, we then come to this particular region, and we then say, now, we then have replaced, instead of looking at too many particles like this, but we take one simple particle and use the y tilde and x tilde. Now we then say, okay, we replace all these individual particles by a single equivalent resultant weight having a defined point of application, and therefore we have y bar and x bar. What is x bar? This x bar is parallel to the x-axis here and the y-axis here, and we have the z-axis over there. Okay, so this is very interesting. Now we're looking at this particular object that is actually in the x, y, z coordinate system. Right, so we actually can see we have a point of application of a single resultant weight. Now we can have this here coming to the picture. Similarly, we can look at these as either if one rotates this system and makes it to face downwards, and or for example, if one considers this as the z axis, right? So the z-axis, the y-axis, and the x-axis like this. Now here's the object. It's straight down. It is going down. It is going down. It is going down. And now because it is like this, we're able to see that, okay, we have replaced the weight of the particles by a single equivalent resultant weight that is straight down for an object that is sitting in this particular coordinate system there. All right, so and now when we do that, this resultant weight actually tends to have a defined point G of application. Tends to have a defined point G of application, which is straight down. Anyway, well, the weight is straight down itself, and the point G of application constitutes the most desired center of gravity that we search for in the objects all the time. Let's move on. Once again, I mean, you don't need to copy everything of this. You'll receive this recording and you can be able to write the notes during your own leisure and so on and so forth. Okay, so it's okay. We need to speak more about the notations we shall use in the calculations, but also when we do past tests, past exams, the tons of them. Okay, we have tons of the past tests and past exams. We shall run through them, not only on the centroids in the center of gravity, but also the mechanics part. Okay, because this module has two major components, has these centroids, etc., and also has the mechanics component. Now, this center of gravity and center of mass for a system of particles. Now, the center of gravity. Let's speak more about this. First point, the resultant weight is equal to the total weight of n particles. So in other words, the resultant weight, which you call like weight subscript r, is the total weight of n particles. Because it is the total weight of n particles, it is the sum of all the weights of the individual particles of the n particles. We take the summation of all those. Taking the summation of all the weights, then we are able to get what we want by taking the summation. And by taking the summation of the weights of all the particles, we get what we call the resultant weight. Sum of moments of weight of all the particles about x, y, and z axis is equal to moment of resultant weight about these x's. Let's speak about the sum of moments, because the sum of the weights of the particles here constitutes, if you add all the weights, you get the resultant. Okay, this doesn't sound new. In particular, it's not very new, because to get the resultant force, what do? We just obtain the vector sum of all the forces. Then we are able to say the vector sum equals the resultant. Now, the sum of moments of weights of all the particles about x, about y, about z axis, about the three axes. So the sum of the moments about the x axis, the y axis, and the z axis, which have determined these moments here, it's equal to moment of resultant weight about these axes. So in other words, the moment of the resultant weight because we found the resultant weight. From the resultant weight, we get the resultant what? We get the moment of resultant weight about these axes. So we first get the resultant weight. After having obtained the resultant, which is W subscript R, which is the summation of all the weights of the particles. Okay, we pay attention now, because after we found the resultant weight, we then proceed to then say the sum of moments of weights of all the particles about X, Y, and Z axis is equal to the moment of resultant weight about these axes. So if we sum the weights, the individual weights, and then we sum the, okay, we have an object like this. Here it's a particle. Then we will consider its individual, it's small weight, and then obviously there are too many particles there, and then these too many particles, each one of them has its own what? It has its own weight, right? And this weight is straight down, right? It's straight down. And so even this has its own individual dW, and so on and so forth. So, but now if we want to find the resultant weight, we add all these weights, right, for the end particles. Now we then say the sum of moments of weights of all the particles about X, Y, and Z axis is equal to the moment of resultant weight about these axes. So the moment of resultant weight, so to find the sum of the moments of the weights is the same as saying what is the moment of the resultant weight. Instead of looking at the individual things here, the individual particles, we just say what is the moment of the resultant weight. That's what we say. We continue. Now, summing moments about the x-axis. Let's speak about now summing moments about the x-axis, which are, now we are summing the moments of weights, about the x-axis, about the y-axis, about the z-axis. Now, let's speak about summing moments about the x-axis. So now, to sum the moments about the x-axis, what we then say is that it is the x component, x bar, which is the x component of the centroid, times the resultant weight is equal to the summation. It is equal to the summation of the, as we said already, right? So if you have this particle here, now this particle here is such that you have the coordinate system, right? Z, Y, X. We saw that here, Z, Y, X. Here is an object there that sits there. Let us visualize what is happening. Here is an object of arbitrary shape. We take a particle, just one particle. It's enough for us to study what we're talking about. And then now we agree that there is a dW, which is the individual weight of this. And then because this one here is just one particle, what do we do with it? We're interested in determining its position. So now, if you have its position somewhere there, then we can be able to consider this. We can be able to consider that, and we can be able to consider exactly this. This one is parallel to the y-axis. This is the y-axis. Parallel to the y-axis is called y tilde. Okay, for this individual particle, right, parallel to the x-axis is called x tilde, and this one is z tilde. Okay, these are sort of the distances that allow us to determine and describe with utmost precision the actual position of the particle in space. Okay, so this is what we do. But now we then look at this and then say the particles are many. The particles are what? Are a lot. So for any particle we choose, so we're gonna choose some particles, so you'll understand how we decide on those choices. Then we can then say, okay, for the summing the moments about the x-axis, along the x-axis, maybe there's another particle because this object is big and it runs across here. You can have x1. Okay, you can call this x1, and then there's another one called x2 for another particle, and then there's another one called x3, x2 tilde, x3 tilde, x4 tilde, and so on and so forth. But now each of these here has its own weight, in which case, therefore, you shall say that for x1 times weight 1, x2 tilde times its the weight of that particular particle, and so on, until the nth particle times the weight of that nth particle. Summing the moments about the y-axis is not different. You take the y bar. So this, I know that it's a bit tiny. It's y bar times w subscript r. And what is the meaning of this? So this tells us that we're dealing with the y component of the centroid. It is therefore times the what? The resultant weight, which is y1 tilde, w1, but y2 tilde, w2, blah, plus dot, 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 yn tilde, wn. wn. All right. We continue. We continue. Right, and we can do the same with the z. This is x, y, and then we can do the same with the z. Right, although the weights do not produce a moment about the z-axis, this is very important for the center of gravity. Although the weights do not produce a moment about the z-axis, because we're dealing with weights. These weights are like downward, so they don't produce actually a moment about the z-axis. So they produce moment about the x and y. By rotating the coordinate system 90 degrees about the x or y-axis with the particles fixed in it and summing moments about the x-axis, we can say, once again, by rotating the coordinate system 90 degrees about the x or y-axis with the particles fixed in it. You rotate the coordinate system with the particles fixed in it. And summing the moments about the x-axis, we're able to say, right, we're able to then say, we can be able to actually obtain the center of gravity associated with the z component, which is z bar, wr, which is z1 tilde, w1, z2 tilde. What is this z1 tilde? It's the position of that particle along the z axis, right, along the z axis. And now as a consequence is multiplied by its weight. Particle 2 has its own position, z2 tilde times w2 plus dot, 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 and then the nth one, zn tilde times wn. Generally, this is what we actually can be in a position to state here. Generally, we can be able to state the following. So we can be able to say, in general, the x bar, these are the general formulae for the coordinates of the centroid. All right, so for the coordinates of the centroid in a three-dimensional system, what do we say? Generally, we then say x bar is equal to the sum of x tilde m divided by the sum of m. And then now we also have the y bar. And y bar is the summation of the distances for the individual particles times m divided by the summation of all the m values. Z bar is the summation of z tilde m divided by the summation of m. Center of gravity and center of mass for a system of particles. Center of gravity and center of mass for a system of particles. Right, center, the center of mass. Provided acceleration due to gravity g for every particle is constant, then, okay, we're saying here, if the acceleration due to gravity, what you call g, if g is constant for every particle is constant, then we say the weight is mg like we do in school. But now we proceed to then say now x bar is the summation of the, okay, once again, we're discussing the center of mass. right? Which means that x bar is the summation of the x tilde m divided by the summation of m. What is this x tilde? This x tilde is just the distance from the origin along the x-axis to the particle. Right, and we do the same here. This one is the distance parallel to the y-axis, and this distance parallel to the z-axis. And now it's divided by the summation of the m. Summation of the m. Okay, by comparison, the location of the center of gravity coincides with that of center of mass. Woo! This is good news. By comparison, we're mentioning the center of mass. But by comparison, the location of the center of gravity, which is the summation of the W's, coincides with the center of mass. Okay, we're dealing with the W's here. But once again, obviously dealing with the center of gravity would mean what? Right, would mean, therefore, you would have x bar is the summation of x tilde W divided by the summation of W. That would mean y bar is the summation y tilde W, summation of W. Z bar is the summation of Z tilde W divided by the summation of W. Okay, so this will sort of be the formulas you would use for the center of gravity, right? And so as much as this was written in terms of M, but every M is W. But obviously this applies for the M is used for the center of mass, the center of mass. Okay, and this one here with the W would be the center, right? Center of, right, the center of gravity, the center of gravity. Okay, so just take note of that, the center of gravity. Let's move on. Once again, we reiterate, we repeat the fact that by comparison, the location of the center of gravity coincides with that of the center of mass. So these are the same. Particles have weight only when under the influence of gravitational attraction. Particles have weight only when under the influence of gravitational attraction. Whereas center of mass is independent of gravity. We repeat, particles have weight only when under the influence of gravitational attraction. So we speak about the weight in general when we actually are speaking about particles under the influence of gravitational attraction. If there's attraction by gravity, then we speak of the weight, whereas the center of mass is independent of gravity. We can see the center of mass. This is the formula. It is independent of gravity. There's no weight here. There's no W there. There's no gravity. There's no gravity. There's no W equals mg there. It's just mass only. Take note of that. We proceed to the next point. Once again, we're recording this discussion here, and you will have access to this recording just a few minutes after we conclude our discussion. You'll actually receive this recording. You can play around with it. The center of gravity and center of mass for a system of particles. Right now, for the center of mass, a rigid body is composed of an infinite number of particles. We acknowledge that as much as we are speaking about n particles, but a rigid body, a brick, a concrete block, these objects we study in engineering, a rigid body is composed of an infinite number of particles. Infinite number of particles. So the particles are too many inside these objects. They're like infinite. We can't even finish counting them. Okay, these particles are obviously, I mean, this is old, it's an old science investigative question to then say how many particles are there. So now it's you subdivide this particular object to the point of the atoms and so on and so forth, and you're able to realize that you have an infinite number. You have one block of concrete, but you can like subdivide it, you can crush it into fine powder. Like if you look at a bag of cement, how many particles are there of the powder? Cement is a powder, okay? Obviously, it can be hardened into a block, but now cement itself in powder form, how many particles are there in powder form, for example? Right, so we then say a rigid body is composed of an infinite number of particles. Okay, so yeah, but I mean, these objects obviously have infinite number of particles. Then you divide them tiny, 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 tiny particles. Consider arbitrary particle having a weight of dW. Once again, we then say there is a particle of weight dW, which means that its mass is dm, and this dW is actually the an arbitrary particle of arbitrary weight. So it's like a small weight. That's what this d stands for, like a differential in calculus. Right, you then say with that, then you can consider dW, and that is the dW that's coming there, dW that's coming there. And then now the dm that appears there is actually, once again, the mass of the arbitrary particle that is so tiny. And two things become very important. Look at the structure. This is the z component, the z-axis, the x-axis, x-axis, y-axis, the z-axis. Let's look at the particle. This particle is awesome, giving us y-tailed, x-tailed, z-tailed. So yeah, this particle here it's this particle, and this particle here, its position parallel to the y-axis is y-tailed, parallel to the x-axis, it's x-tailed. And this is the z-axis, and we're measuring the distance from the xy plane to the position of the particle, and this is vertical distance. This vertical distance or vertical displacement is called z tilde. Now, this is just for an arbitrary particle, just a random particle. You can choose it here, you can choose it there, you can choose it anywhere. But it's having a weight dW, and therefore its mass is actually the same as dm. Now, we then say we can be able to find the center of gravity for this object and the center of mass. Okay, they coincide, please. They coincide and they're the same. The center of gravity and the center of mass for the object to study. So now, we then have here y bar, x straight bar, z straight bar. So once we use the straight bars, they're different from the tildes, because now they mean that now the y bar, the x bar, the z bar, they define the actual center of mass, which is the same as the center of gravity. So it's something that you need to take note of, because this is critically important. So it's something that you need to know. Take a look at that. So we're good. We're so good. We're so good. Okay. Okay, we're good. We found the center of mass. Center of mass, CM. And it is that center, the dot there. And now, because we need this position, we are looking for the centroid all the time. So we are looking for the distances, like the y bar, the x bar, the z bar. They all define the center of mass. Please, this is awesome news. So now we then say the x bar equals the integral of x tilde dw divided by the sum of, rather, the integral of dw. Okay, remember that here we spoke about the summation. So we convert these things to integrals because these summations are going to take us forever to do. Instead of really saying here, we are dealing with the sum of all the W's. We say the integral of dW, the integral of x tilde dW. So in other words, we have the following over here, and we then say, what is x bar? It is the integral of x tilde dW divided by the integral of dW. Okay, but yeah, I mean, my point is, in the end, this, we first defined it as a summation of x tilde W divided by the summation of the W. But now, obviously, I mean, we're dealing with with an arbitrary particle of the weight dW, meaning that we can actually be in a position to state this formula. So from this, this is the most general, because this integral symbol, the integral means sum. But yeah, we are speaking about an infinite sum here. That's what we're talking about. Okay, so that's something very, very important. But we're able to therefore switch between the two. Okay, we first define this in terms of the sigma notation. And the sigma notation is very much elaborative of the fact that, okay, we're dealing with something important. We're dealing with what? We're dealing with a particle here, and then we can, or an infinite number. First, we say a finite number of the particles, maybe like n of the particles, and then we add the individual weights of this. But yeah, in general, then we look at the fact that, hang on, a rigid body is composed of an infinite number of the particles instead of it, because now then we can't say they're only n, they're infinite. Consider an arbitrary particle having a weight of dW, because now these are infinite, we resort to the integral, and the integral means the infinite, the integral means the sum. So we're still summing the actual moments. Okay, we are summing the moments. What are these moments? The moments about the x-axis, the moments about the y-axis, the moments about the z-axis, and these moments, now we then say this distance the parallel to the x-axis, which is the x tilde, we then multiply it by the weight of that particular particle. And this is like, if you look at this, if you multiply force, right, you take displacement and you multiply force by it, what you get is what you call the moment. Right, is what you call the moment of that particle. Okay, we do this for the moments about the y-axis, about the z-axis, and so on and so forth. Okay, we need to move on to more examples on this. Okay, before we look at the examples, it's not only that we spoke about the center of mass, the center of gravity, but what about volume? What about volume? Because the center of gravity and center of mass for a system of particles, we discussed the center of gravity and center of mass for a system of particles, there's something we call the centroid of a volume. Because now we can be interested in saying, okay, how much volume do we have of this particular substance? So the centroid of a volume, consider an object subdivided into volume elements, dV, for location of the centroid. You consider centroid of a volume, centroid of a volume. Consider an object subdivided into volume elements. So to find the centroid of a volume, what do we do? Because you need to be able to find the centroid of a volume, and hence the theorems we're going to do. Right, the theorems we're going to discuss. The theorems by Pappus. Right, for example, first, we then say consider an object subdivided into volume elements, dV, for location of the centroid. For location of the centroid, we then say, okay, here is an entire body, and we now, okay, I'm going to look at a small particle. We cut small. We cut tiny. And then we say, okay, that's a volume element. But there are too many of these particles. We can look at like so many volume elements there, like an infinite number of them. And then now we're able to get the coordinates of the centroid, which is the centroid of a volume. What is the centroid of a volume? It is therefore equal to the integral of x tilde. So now look at this here. I want to speak about this. So for this particle, this is y tilde. And because this is the y-axis, x-axis is that. This, okay. And then this guy is x tilde. For this particle, we use the tilde symbols. And then obviously now we're dealing with this particle here. If we're moving, because we measure it in 3 dimensions. In the 3 dimensions, if this is the position of the arbitrary volume element, we then say parallel to the x-axis is x tilde, because the particle is somewhere there. So we travel x tilde. Okay, we travel y tilde, but we must go up z tilde. So this one is z tilde. Okay, now let us discuss this a little bit more, because now we're discussing the centroid of a volume. Right, centroid of a volume. Once again, we'll cover all these topics, please. Centroid of a volume. So we have like z tilde there. And these all together, they sort of go on to describe the position of the particle over there. Position of a particle over there. We continue. We continue. All right. We continue. Okay, so now then we actually therefore can find the centroid of a volume. So the centroid, if the centroid is C, then we know very well that we really can say, okay, parallel here is y bar. This one becomes y bar, and this one becomes exactly x bar. That is x bar, this one. And also now we move vertically upwards, and this one that moves from here to there, the position of the C is actually Z bar. And these straight bars, not the tilde symbols, they describe what we call the centroid of a volume. Centroid of a volume. Centroid of a volume. So we continue. The centroid of a volume. The centroid of a volume. So we continue. We continue. We continue. Next point. There's something we call the center of gravity and center of mass for a system of particles. We've been speaking about this as much as now we spoke about the centroid of a volume, but still our focus on the center of gravity and center of mass for a system of particles. Right, so for example, the centroid of an area. Okay, this is very important. We speak about the centroid of an area. We spoke about the centroid of a volume, the centroid of an area. For centroid, for centroid, for surface area of an object such as plate and shell, subdivide the area into differential elements. Subdivide the area into what? Into differential elements. dA. Right, for centroid, for surface area of an object, such as plate and shell. Okay, so we can look at plate and shell. Plate and shell. Right, so for centroid, for surface area of an object such as plate and shell, subdivide the area into differential elements, dA. Okay, so we're looking for the centroid of an area, and for centroid for surface area of an object such as plate and shell, and we're dealing with areas there for the plates because those plates are 2-dimensional. So we speak about the surface area there, and also the shells themselves are basically 2-dimensional. So subdivide the area into differential elements, dA, And if you can divide the area into differential elements, dA, these are the differential elements, dA. So the dA, like we saw with the dW, with the dm, they're like small areas, right? So if you have that, you then would be in a position to say, here is the y-axis, here is the x-axis, and therefore this is a curve. This curve is actually a function y equals f of x. The center C of the what? The center C, which are the coordinates of the centroid, or which is the centroid itself. And then now we're able to have the x bar, y bar, and this define the centroid of an area. But how do we do it? We then say we can take a vertical slice. Okay, if you take this vertical slice like that, right, taking the vertical slice, and we're dealing with, we take this vertical slice and we put it on the what? In the XY plane. And then we have this one here. And then we have this one, the center, which is y bar, which is y over 2. All right. Yeah. So if we then say the entire length of this, if this is like a rectangle, okay, the length and then the breadth of it, right? So we can look at the small change, some small length along the x. We call that partial x. We call it like dx, right? And therefore this is the curve y equals f of x. And this is exactly xy. So now, if we then say we are able to determine what actually is mostly needed, right? So if we want to determine with precision, there is a particle there. There is a particle here. And this position describes the center, because if the rest is y here, then we can say y out of 2 is actually what we need. Right, so, I mean, if we are to say this is actually the center of this particular rectangle, but because it is a slice, we're going to call it what? We're going to call it y tilde. And also, now we're going to look at the distance. We can look at the distance horizontally. Right, if you look at it horizontally, the distance from here to here is x. And therefore now we can look at it x tilde, which is x out of 2. Okay, if you're looking for a horizontal slice, right, which is just an area of this. This is like area, so you're looking at a plate. If this is like a plate, and we can be able to cut a vertical strip and then a horizontal strip there. But now this one here becomes like a dy, the small change there, and this one becomes xy, and then becomes y equals f of x. And therefore now in the end it becomes y tilde equals y, like that. Okay, yeah, for the vertical. But remember, this is not the center of the centroid of an area, right? Because it's just for a strip, so we're gonna say y tilde is y out of 2, and therefore if this one here is also horizontally, the distance from here to there is x tilde, which is what? Which is just we call it x by choice. And then now here the half, because if the whole thing is from here to there, it's x along the x-axis, we can divide by 2. Okay, why do we divide by 2? We divide by 2 because it is just an extension of the concept of what is the length of a line. Okay, so if the line is on the x-axis, and now you then say the distance from here to there is x. What is the distance in the middle? The distance in the middle here, you have x over 2, x over 2. So that is sort of what happens here. but we use this. But now let's take a look at these formulas here. So if you then say you're taking the differential elements, because you're taking these elements here, you're taking these elements right now, you're able to determine the area. Right. So now, which means that now you're going to say, here it's the x tilde, y tilde. Okay, for the x component, you have x tilde dA divided by the sum of the dAs over the area A. And then for the y component of the centroid of an area, we actually speak about the formula for y tilde dA divided by the integral dA over the region A, over the area A. And also for the z component, we do the same and say, okay, the distance, the actual distance there, the actual area of that element, dA. So because each element has an area, like this element has an area, this element has an area, and therefore we're able to find the area, and that area is multiplied by the z tilde. We divide by the integral of the dA. So these are sort of the centroid of an area, three formulae that we're going to use. The three formulae that we're going to use. Okay, we're going to do examples on these things. It's not... Okay. You sent me one question about the center of gravity, the center of mass for a system of particles, but now you looked at the wire question. So we're going to discuss the wire question and see how this wire question works, but also we can have a perfect opportunity to practice and try a wide range of problems that are of the best interest to us. So we proceed most definitely as follows. Right now, for the center of a line, if the geometry of the object takes the form of a line, if the geometry of the object takes the form of a line, the balance of moments of differential elements dl about each of the coordinate system yields the following. So you have the x bar. So let's look at this wire. If the geometry of the object, we're looking for the, okay, we're speaking about the center of a line. Before the center of a line, we spoke about the centroid of an area. And before that, okay, we're going to write some tests with us. Okay, I'm going to give you some pop quizzes. Okay, so when I give you the pop quizzes, you must be ready to try the pop quizzes and we shall solve the pop quizzes. So that is something that is very, very important. Okay, so it's not that we're just discussing these things. So we are doing these things and then we shall discuss everything. But now the pop quizzes are coming. There are some pop quizzes that we shall give you so that when you get back to the class, you're able to follow on these things and you do not just forget, etc. So because practice makes perfect, these things we shall solve some problems together, some you shall try. But now we want to speak about the centroid of a line. If the geometry of the object takes the form of a line, right? If now we do not have a volume, but we just have a line, and then now the geometry of this object takes the form of a line, the balance of moments of differential elements dl about each of the coordinate system yields. So the center of a line, we take a line, the blue one. Right, now the line has some length. Right, so we have the differential elements dl. What would dl be? So dl would be some small length, like dv, like dm, like dw. So these are like small quantities, right? So for the line, if the geometry of the object takes the form of a line like this, you can take, and the line is of length l, you can take a small section of it and call the length dl, just a small length. And then if that is the case, then you can be able to draw this kind of a triangle. Okay, you looked at something like these before yourself, and this is dy dx, and we shall look at lots of questions like this. And then this one here is dl. Pay attention. This means at this point, we have the following. This is y and this is x. So what do? We then say that for the x component, if then there are two things, we always do it in two ways. Here is this way, and we take a particle, a random particle there, a random particle. So a random particle, first we determine, because it's a random particle, its position is y tilde x tilde, and then now we then say its length, associated length for its section of that wire, it's dl. And then now we can be in a position to then say, right, then the balance of moments of differential elements, dl. So the balance of moments of differential elements, dl, about each of the coordinate system yields the following. So you would have to look at the fact that now if this is x tilde, this x tilde, you then can be in a position to then say it is x tilde dl integral over the line of length L divided by dl over the length L. But also now for the y component of the centroid of a line, okay, you would have to take y tilde dl and over the line of length L divided by dl over the line of length L. What about the z bar? What about the z bar? Okay, so the z bar is z tilde dl divided by the integral of dl over the length L. So obviously, I mean, the z component now takes care of this is only the xy coordinate system, but the z component applies in the three-dimensional case. We're taking a look at the wire. And now we're saying, okay, instead, the geometry of the object is the form of a line. So now we then say, okay, we can find a particle, but what is the position of this particle? This is the x-axis and this is the y-axis. So we then say it's x tilde here, the position, the actual position. We want to find the coordinates. And then now this one is y tilde. And then now the centroid is sitting there. The centroid is sitting there. If the centroid is sitting there because we're speaking about the centroid of a line, then we can then say it is x bar, y bar. And this x bar, y bar would define the actual position of the centroid. So that now x bar is the integral of x tilde dl, the integral divided by the integral of dl, and so on and so forth. We have the following. Okay, now we have an example. We're looking at an example. Right, so looking at an example, the couple of things that we need to take into account, and we proceed as follows. Right, in this example, we want to practice and try something. So this example is very popular, and I think that you actually have sent me something similar to this one, and therefore we shall actually obviously take this into account and make sure that we're able to proceed with so much ease. And yeah, it is the sort of example that you sent to me, and we have a perfect chance to discuss it. So, right, so locate the centroid of the rod bent into the shape of a parabolic arc. This is a rod, and it is bent into the shape of a parabolic arc. Okay, if this is the rod and somebody bends it into the shape of a parabolic arc, now we are then saying, let's take a particular segment of it, and now it is long, but we take a segment of it, and this segment of it, then we call it y tilde is y for the actual position parallel to the y-axis, and then we also have x tilde, which is x, the actual distance from the origin parallel to the x-axis, parallel to the y-axis. Okay, and that defines the x tilde, y tilde. And then right now, we then have dl. So which means, therefore, we have y and we have exactly x as a consequence of these. Okay, now what then do we do? What is dl? DL. So this DL, we know that we're dealing with a wire of length L, and then we take a segment of it whose length is DL. And then now, if then we then say, okay, the position of this particle here would be X tilde Y tilde, so that this is X tilde, distance from here is X tilde, so that we have X tilde here. And then now the vertical distance here from here to the actual height is Y tilde, and this is X tilde Y tilde. Now, its length, the length of this segment of the wire is just DL. Now, there's something very important. The actual centroid of the wire, because we mentioned that the centroid of a line is actually of interest, and we use these particular formulas using the integral there. So now we then say, right, the actual centroid of the rod can therefore be determined. Right, so obviously at this point, if this is the center of the centroid, then C would have the coordinates X bar, Y bar, but the straight bars. And the equation of this is X equals Y squared. X equals Y squared. X equals Y squared. Okay, let's proceed. Let's proceed. Now, okay, if we then say in this particular diagram, the horizontal distance to this particular point is 1 meter, and here it is 1 meter. But the arbitrary length here is Y, and here it is X. But now this is 1 meter, 1 meter. We're good. But what then do we do? We want to locate the centroid of the rod bent to the form bent into the shape of a parabolic arc. Let's look at this particular example. Let's look at this particular example with the differential element located on the curve at the arbitrary point XY. Right, we're speaking about the differential element. Okay, here is a differential element. There it is. There is a differential element there, DL. And we're able to see that there is X tilde Y tilde there as the actual coordinates of the point, which describe the position of the point in the two-dimensional space. Okay, so right now located on the curve at the arbitrary point XY, located on the curve at the arbitrary point XY. That is a differential element. It is located on the curve at the arbitrary point XY. Okay, we can see that it's located on the curve at just the arbitrary point. We can choose it there, anywhere. Okay, we're good. Let's speak about two things. The area, but not only the area, but the area and moment arms. For differential length of the element DL, differential length, okay, we saw that the differential length of the element DL, we saw that the wire itself, its segment is DL in length, vertically is DY, and horizontally is DX. That is what we know. Okay, we saw that exactly in this part here. Because this is the x-axis, horizontally is DX, vertically is DY, and also along this the wire, because we're speaking about the centroid of a wire. In that case, it's a rod in our case, which is just a thick wire anyhow. Obviously, then we have DL there. All right, now we are able to perform the algebra. So this one is a right-angled triangle, and therefore we're able to use Pythagoras theorem, which is DL squared is equal to the same as what? Is the same as dx squared plus dy squared. So we're able to find the length. We want to find the length of the hypotenuse, so that dl, we take the square root of this, which is dx squared plus dy squared. We shall do quizzes together, please. The quizzes will be sent on WhatsApp at the appointed time when we will be in a position to, when we've done enough examples and the concept is very clear, we shall obviously just send you quizzes on WhatsApp. You try those and we're able to mark them and be able to just track our progress there. Okay, we're good. Right, so the area and moment arms. So now let us discuss the area and moment arms for differential length of the element DL. What is the DL? What is DL? We have seen that using Pythagoras theorem, DL squared is dx squared plus dy squared. Solving for DL, making DL the subject, take the square root of dx squared plus dy squared. What is this? What is this? DL is dx squared dy squared, which means DL we then are able to perform algebraic manipulations here. Okay, we want to get, so there are at least two ways. Okay, we can find more. We can first be able to perform, we factorize the interior, and we're able to take out dy squared as a common factor. And if we do, we shall have here dx dy all squared plus 1, like this. So we can be able to take the dy squared. And if you take out the dy squared, then we have this. If you factorize, because if you multiply it by the dy squared, then you're going to get back to that one. Okay. Now, this one here becomes the square root of dy squared, the square root of dx dy squared plus 1, which means that dl is, right, so you can be able to see the square root here, which is actually dx dy, and you square these plus 1, the square root of the dy squared. What is the square root of dy squared? It's just the dy. And hence, this is actually what we have. So this confirms that the dl is the square root of the dx dy all squared plus 1, and then the dy is outside. Take a look at these. This is very, very important. Okay, and we move forward. Right, so moving forward, what more are we able to obtain out of this? We're able to see that we remember that at this point, this curve is x equal to y squared. It's x equal to y squared. So we can be able to perform some differentiation here. Because if x is equal to y squared, in this particular expression, we need dx dy. So we can be able to get dx dy, and dx dy is 2y. Dx dy is what? Is 2y. Dx dy is what? Is 2y. Now, if dx dy is 2y, then let's perform substitution into this particular formula. So obviously, if we perform substitution into this particular formula, we're able to see that if the dl is actually the same as dx dy squared plus 1 dy, means that dl is the same as what? What is the dx dy? Right, the dx dy is twice y, and you square this. Plus 1, and you have a dy. You have a dy. So that now dl is the square root of what? So what is the 2y all squared, which is actually 4y squared plus 1 dy. Okay, which you can write as the 2y all squared plus 1 dy, and this is the L. Now, what is then the centroid, and what is the actual location of the centroid? Now, you refer to the shape here, and note that in this example, the examiner told us here that the actual position of the centroid, because this was arbitrarily chosen, arbitrary position of the of this particular element, right, of this differential element, is y on the y-axis, x on the x-axis. So x is x tilde, y is y tilde. We proceed. The centroid is located as, we're saying x tilde is x, y tilde is y. Okay, let's look at the examples and integrations. Examples and that pertain the integrations that we need to do here. What are the integrations that you need to do here? First things first, let us look at the fact that the x tilde is given by x tilde dl divided by the integral of dll. So this is the formula we use, but let us analyze this formula together. So if this is the formula, what then are we able to achieve here? We're able to achieve that this is exactly the integral. Remember that the actual length of this wire, the total, it's from 0 for the origin up to 1, and also this. So in other words, we have that x is between 0 and 1, but also we have that y is between 0 and 1. So x is from 0 to 1, and then also y is from 0 to 1, like this. So now, because of this, then we're able to make the observation that at this point here, you're going to integrate from 0 to 1. What is this differential element? We have already been told in the question that the x tilde is x, but also the y tilde is y, meaning in the place of the x tilde, what do you put? You only put x. What is the dl? Okay, the dl you already know, right? Because we've already called that one here. What is the dl? The dl is the square root of 4y squared plus 1 dy. So this is what we're going to substitute in the place of dl. We put 4y squared plus 1, and then we put what? We put a dy. We put a dy. We put a dy. And then now you divide this by the integral of the dl, okay? But we integrate from 0 to 1 still, okay? Because, okay, the y, remember, it's from 0 to 1 also, as much as the x is, right? So you have exactly that one there. So this is obviously for the x, and now we're able to say the dl is actually 4y squared plus 1, 4y squared plus 1. That we put here our dy, for example, right? Our dy, for instance, because we're able to see that the dl is equal to what? The dl is 4y squared plus 1 dy. All right, so we're good. We awesome. Now, what is the meaning of these here? What is the meaning of this? This is easy, because you already know the integral from 0 to 1, but also, we know that x is y squared. It's the graph. X is y squared. X is y squared. Here it is. X is y squared. Because x equals y squared, then we're able to do it. Because wherever there is x, you can put y squared. The integral of 4y squared plus 1 dy. We divide everything by the integral from 0 to 1 of 4y squared plus 1 dy. Like this. Like this. Okay, we're good. Now the question then is, what do we do at this point? And how do we then evaluate these here? So evaluating these, it's something very, very easy, right? So we perform the calculation as follows. We actually need to perform the integration of this, and you need to perform the integration of that, right? So, but we're yet to spend a bit more time on the integration techniques, all right, because the integration techniques, they form the basis of this reasoning. And then we then say, what is the integral from 0 to 1 of y squared, the square root of 4y squared plus 1 dy? It is 0.6063. Okay, so we're going to spend a bit more time on this so that you can actually get to know how to perform these particular integrals, and we shall use a couple of substitutions. What is then the integral of 0 to 1 of the square root of 4y squared plus 1 dy? So this integral here is the same as 1.479, and you are able to get that. Okay, I want to explain something here. Right. So this is something very, very, very important. Right. So now, so there are a couple of things that you need to take into account when it comes to this particular, there are rules that I want to mention now. Right. So there are rules that I want to mention in line with these so that you're able to take note of the rules. You're able to take note of the rules that remain important for us. Important for us. Right. Normally we use the tangent here. We use the tangent. Right. So you can use the tangent to be able to perform the calculations. Right. So if you use the tangent to be able to perform the calculations, right, it is therefore possible. For example, how can you be able to do this? So yeah, we can actually spend a little bit more time, just a split second. I want to make sure that this is made very, very clear. For example, how do you therefore perform any of this? Let's perform maybe this one denominator. Right, in the denominator, you can let, right, because it is exactly like this. If you want, you can write it as like how? Right, you can write it as the integral from 0 to 1 of 2y squared plus 1 dy. So you let u be 2y, and then du is 2 dy, something like this. Okay, you can do that. Or differently, I mean, there are too many ways to do that, but I feel that that's something you can do. Right, if you do this, what are you able to achieve? Or I think that the best is we're very smart. We can perform just smart algebra. You can just pull out, just factor out the 4. Factor out the 4. Right, because if you have the integral from 0 to 1 of the square root of 4y squared plus 1 dy, then you can factor out 4 out of this. Okay, and then you have the integral. You factor out 4, and then you have y squared plus 1/4 dy. Okay, the square root of 4 becomes 2, 0 to 1, y squared plus 1/4. Right, so if then we need to solve this one, if you want, then you can be able to take, can let, right, you can let y be equal to the tangent. You can let y be equal to the tangent. Right, so if you let y to be equal to the tangent, what then are you able to get? Doesn't matter. Let y be equal to the tangent of theta, for example. Right, if y is equal to the tangent of theta, then what is dy d theta? So dy d theta is going to be sec squared theta. Okay, let us play around with this. It's something I want to elaborate on here. That is something very important. So you get that, but when you get that, what then can you be in a position to achieve out of these? Okay, there are too many ways to do it, but this is just one way. Okay, just one way. But the answers will be the same at the end of the day. Maybe we can do like the one denominator, then the one denominator in the numerator is the same, so that you can just show how you can get the 1.479. Right, so now when you have that, then you would have this, and obviously dy d theta is the secant squared of theta, which means when you have the integral of 2 from 0 to 1, and now you have the y, which is the tan squared. Just bring it down a little bit. Just below this orange line. So you have the integral. Okay, you can change the limits of integration here and have, for example, this one, the y, wherever there is y, you can put 10 squared, which is actually exactly 10 squared. So you can see that you would need to do something extraordinary to actually make sure that this and that are the same. This and that are the same. So you can put 1/2 here. Right, so if you put 1/2 there, so let y be 1/2, 10 theta. Right, if it is 1/2 10 theta, if you differentiate, it is 1/2 the secant squared theta. Okay, yeah, because I want these to be the same thing, doesn't matter. So that in the end, then now you're going to put here, because you want to have just 1 under the square root. So that here now, in the place of the y, you're going to put 1/2, 1/2 10 theta, and then you square it. And then you have 1/4. 1/4, and then you have dy, like this. Okay, there's a 2 that sits outside. Why am I putting the 1/2 10 theta? Because we want to make sure that this substitution works, but also want to make sure that the 1/2, when you square it, it becomes 1/4, and therefore the 1/4 is good. Okay, we're going to put some limits of integration just in a split second. But now if you square this one, it's going to become 1/4, 1/4, and then if you have 1/4, 1/4, take 1/4 out, it becomes 1/2. And then you have the 10 squared. Okay, you can write this one as the 10 squared theta plus 1 dy. Meaning that, therefore, if you have
Sorry,
the integral,
sir.
yes, please.
Yes, you left out the thingy, y squared next to the square roots.
Okay, yeah, okay, I get your point. I'm looking at only this one.
Okay.
Denominator. Yeah, I'm looking at only the denominator because I think it's the same thing. Okay, so we can decide, we use the same approach for each one. But yeah, I decided to start with the denominator. Okay, just to show the method. And then the same is going to be used, but this other one I did not like it because it's a y squared. So you'll have a bit more extra work. I wanted us to start with something smaller. Okay, if you like. Okay, so now dealing with only this one, 0 to 1 with the 4y squared plus 1 dy. And then now we actually obviously have that one. So we have the y squared plus 1/4, but now the y is 1/2 10 theta. Okay, so the derivative of the 10 theta is the secant squared. Okay, there's 1/2 there. And in the place of the y, you put 1/2 10 theta. In the place of the y, you put 1/2 10 theta. And then you square it, there's 1/4. Okay, there's too many ways to do these. It's not the only way. Now, once again, if you square the 1/2, it becomes 1/4. But there is also 1/4. And therefore, this is like 1/2. And then it's like 10 squared plus 1. And then you have the dy. So you cancel the 2 and the 2. It becomes the 1. And then now you have this one, the integral. Okay, let's deal with the limits. So now we can draw a small cross like this. Okay, yeah, we're going to do just the denominator, and then we can do the numerator as well. So now here, the y, and then the theta. Okay, the y and the theta, because we're changing from the variable y to the theta variable. So this is also y, then theta. So what is the y? Okay, the y is from 0 to 1. Right, so we substitute into the substitution. Like if you look at the fact that you have y equals 1/2 10 theta. Okay, if y is 0, you put 0 equals 1/2 10 theta, which means that 10 theta is 0. And then theta is arctan 0. And then what is arctan 0? Arctan 0 is 0. Okay, so you have 0. Right, you have exactly 0 there. Next, you have 1. Right, so for example, if we note that y is 1 here as the limit of integration, then you put into the substitution. we're able to realize that you're going to put a 1 here, and which means that we shall have 1 in the place of y equals 1/2 tan theta. And this means that 2 equals tan theta. And then what is theta? Theta is arctan 2. And then we have this. Okay, let's do arctan 2. Okay, we're going to use the calculator for that one, because it's not very easy to just do. Okay, so let's continue and do that one. So we're going to do arctan, shift tan of what? Of 2. Right, so yeah, shift tan of 2. Right, obviously we can use any of this. It doesn't really matter. You can use your degrees, you can use your radians, and the calculator is giving the answer in degrees. Doesn't matter what you use. Right, so because they're equivalent to this. But we have 63.43. 63.43. Right, so we have 63.43. The calculator is actually giving the answer in degrees, but once again, you can actually deal with the answer in radians. So now, meaning obviously we shall integrate from 0 to 63.43 degrees, but once again, you can do it in radians. You can set the calculator differently, which is nice, which is very nice. At university, we don't like degrees, so I feel that we actually obviously have that option. I need to just set the calculator and get the answer in radians as well. So if you do here, you go this, you go shift setup, and then you can go to radians. Right, good, we're in radians. And then you can do shift 10 of 2. Right, so doing shift 10 of 2 gives us this is actually more perfect for us at university level. So we have actually the 1.107, 1.107, which is the answer in what? 1.107. Right, I'm going to write it in green. Right, I'm going to write it in green color. Yeah, 1.107. Right, so the 1.107 is the answer in the degrees. It's the answer, rather in radians, in radians, in radians. So you can say radians. Okay, we love radians at university. Okay, let's just do radians. Right, so we're gonna use the radians and then say it's 1.107. So you can do that. So obviously for the y, it was like 0 to 1, and then here we still have that. Okay, but now there's more we need to do, because what is the 10 squared plus 1? But remember from high school that sine squared, start there a little bit. Okay, we have the liberty to just discuss quickly. This is a very popular identity. Like if you have sine squared theta plus cosine squared theta, the result is always 1. And this means that you can divide both left and right by the cosine squared. So that 10 squared theta, you divide cosine squared plus 1. You divide sine squared plus cosine squared. Sine over cosine is the 10. Cosine squared over cosine squared is 1. 1 divided by cosine squared, if you divide through by cosine squared, you get the secant squared theta. Okay, so that 1 plus 10 squared is a secant squared. You take the square root, which is the secant of theta. What is dy? Right. So dy can be seen from this, which is actually 1/2 secant squared. 1/2 secant squared theta d theta. I'm just doing the denominator because I know this is like a bit long. Right. So in the end, then we get this. And let us actually just finish this off. So now, if we finish this off here, we are able to get the result of this. What is the result of this? What is the result of this? All right, so 1/2, 0 to 1.107. Hey, all right, obviously now I need to use integration tables here. You need to use integration tables, right, in general, because now this is 1/2, you bring the half there, and then now you have the secant cubed of theta, d theta. Okay, this is the problem we have in front of us. But the secant cubed, to do the secant cubed, what do we use? Right, to use to find the integral of the secant cubed, we use the some results we know, like your what? Like your integration by parts. Let us do integration by parts quickly. Right, right, so that now when we do integration, we need to do the integral of that cubed. Right, the integral of that cubed, the cube can be broken down into, I'm going to leave out the limits of integration, and I'm just going to focus on what the answer is to the integration problem. So now you're going to have secant squared theta, secant theta d theta, which is the, now what do we get here? We actually need to break these into parts, need to break these into components. Choose the one that is easy to integrate. So obviously the one that is easy to integrate is secant squared. So you pull out secant theta, and then you have the secant squared theta, d theta, right, minus the integral of, right, then you actually therefore continue to deal with the derivative of this one, which is the derivative of the secant is the sec theta tan theta. Like, I'm just illustrating this method. I know it's a bit long. That's why I decided to focus on the denominator. Okay, in the method is like the same for each one of this, right? And therefore the integral, so you find the derivative of this, and then now you find, okay, I'm using the very direct integration by parts approach, d theta. Okay, now the integral of the secant squared is the secant by secant is secant squared theta minus the integral of the secant squared is tan theta. Tan theta by tan theta, tan squared. So now this is what you get. This is what you get. So then what is the integral of this? Okay, so you need to remember this one. So the secant squared is the secant of theta. What is 10 squared theta? Okay, we know that 10 squared plus 1 is 6 squared, but 10 squared theta is 6 squared theta minus 1. Okay, if you manipulate, 10 squared plus 1 is 6 squared theta. Let's make 10 squared the subject. So it becomes 6 squared minus 1. So wherever there is 10 squared, we're going to put 6 squared theta minus 1. And then d theta. Okay, just squeezing in just the basic computations here. And therefore, this one is exactly what? It is actually 6 squared theta minus, okay, then we have this sec theta, which is the integral of sec cubed theta d theta minus the integral of d theta. No, the integral of, wait, the integral of, okay, now we have the sec. So it's going to be in two places. Sec by sec squared. I'm just trying to squeeze this. I know it's congested. Sec times sec squared is sec cubed. But now you have the sec times 1, which is plus the sec theta d theta, which is sec squared theta minus the integral of sec cubed theta d theta plus, okay, now the integral of this one, the integral of sec theta, the integral of sec theta is the ln of sec theta plus tan theta plus C1, arbitrary constant of integration. Okay, this is what we have. So with this, then we are able to then say this sec cubed theta. Right, the sec cubed of theta is equal to what? The sec cubed of theta is equal to the sec squared of theta minus the integral of the sec cubed of theta d theta plus the ln of sec theta plus tan theta plus C1. Okay, you add these two guys. Okay, upon you compare, you transpose the terms. Right, if you transpose the terms, it's gonna be what? Okay, this minus x cubed and the sec cubed, this is negative, but if you move it across the equal sign, it's going to be positive, giving us 2 of the sec cubed theta d theta. Okay, once again, I left the limits out and just want to focus on integration so that if we're done with the integration, then we can just substitute the 0 in the other limit. Right, so, but this is then equal to sec squared minus, rather plus. Okay, this one we move to the other side. So it's sec squared plus the ln of sec theta tan theta plus C1, which is the integral of sec theta d theta, which is 1/2 sec. So the integral of sec cubed is 1/2 sec squared plus 1/2 the ln of sec theta tan theta. Okay, this one we can divide by 2, but it's going to be C. Okay, so we have found the integral of the cubic secant function. Cubic secant function. So yeah, the integral of the sec cubed is that one. Just take note of that because yeah. Okay, so we're good. We are just finishing this. All right, we're finishing this particular example, but we just want to elaborate on the integration part of it. Right, so integral. So yeah, we're good. Yeah, we are just here, please. We are moving. So yeah, take it very, very easy then. Take it very, very simple then. Right, take it very, very easy. Take it very easy. There's something that I'm checking. Something that I'm checking. Something that I'm checking. All right, so we're good. But now take note of these here. Let me see what, this might be small. Okay, it's a small little typo. So this one must be sec tan because the integral of the sec squared is tan. So this one is going to become sec tan. The integral of the sec squared is the tangent. So this one is going to become sec tan. Let me just write it down. So this is going to become exactly sec tan, not sec squared. It's going to become sec tan. I'm wondering why it became that. So it's going to become exactly sec tan. Okay, this is going to become sec tan. Then you have minus the integral of sec cubed theta d theta plus the integral of sec theta tan theta plus C1. Right, so this one is going to be 2 sec tan. Right, okay, I'm just trying to show. I know that I'm just congesting the things, but you sort of get the idea of what's happening here. And then obviously the same can be used. So now this one is sec theta tan theta. Okay, and then this one is sec cubed. If you add it, it becomes 2 of this. Plus the ln of sec theta tan theta plus C1. So you divide by 2, and it becomes 1/2. Okay, this one is sec10, like we're saying. I'm wondering why it became a square there, but it becomes sec10. Just take note of that. Sec theta, tan theta. 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 Wait, yeah, okay. So now we are then saying the integral of this is going to be sec theta, tan theta, but yeah, it's multiplied by 1/2 of that. Okay, we are moving, please. Is multiplied by exactly 1/2 of that. Okay, so in the end, then you have, okay, divide by 2, sec theta, tan theta, but it's going to be like 1/2 of the sec theta, tan theta. Okay, I'm saying this because then when you get to this point, what is then this integral? It's 1/2 of sec theta, tan theta, sec theta, tan theta, plus the ln of sec theta plus tan theta, 0 to 1.107. Okay, so the integral of the cube is the integral of the cube, right? You can look at it as having 1/2 of that. So let's make it 1/4. Let's make it 1/4. Okay, because there's 1/2 here, but there's 1/2 that's going to come with the integral, so it's going to be 1/4. Okay, we're trying to just squeeze the rough work here, right? So with that, you're able to just perform everything else. So we're just getting the integral of this cubed, which is 1/2, but there's 1/2, there is 1/4 sec theta, tan theta, and then plus that. So we continue. Okay, so now with this then in mind, we're just verifying the answers that are here. Yes, please.
Yes, about the integral of sec theta d theta.
Yeah, the integral of sec theta the integral of sec theta d theta is the ln of sec theta plus tan theta, and we will discuss why this is the case. Okay, the integral of sec theta d theta is the ln of sec theta plus tan theta, right? So that is part of this. So obviously this is the kind of integration that sort of constitutes the basics of integration. But most of the times this will be very easy to do. But I'm sure that this is just one of those integrals that is a bit technical, a little bit. So in which case then, right, we're good. We take these things, and then we have the following. Right, so it means that we then have that the integral from 0 to 1. We're taking the one denominator because I realize that it's going to be a little bit easier than the one with the y squared outside, the numerator one. Okay, because the method is the same. Okay, we use the same method. So, but now then you realize that therefore this integral is you study it like this, but it is 1/4, and then you have here sec theta tan theta plus the ln of sec theta tan theta 0 to 1.107. Can use a calculator for this. 1/4. Okay, first we substitute the 1 point. So you're going to have sec 1.107, the tan 1.107 plus the lean of sec 1.107 plus the tan 1.107, and then yeah, that's the thing, and then minus 0. Okay, because if you put the 0 here, it's going to be 10 0 times sec. Sec 0 is 1, but 10 0 is 0, so this is going to be 0. 10 0 is 0. Sec 0 is 1. The lean of 1 is 0. So the minute you substitute the 0, everything is going to be 0 there, so it's just minus 0. But now the most important thing that's going to count is the substitution to the integral of the 1.107. Okay, now this one needs a calculator. Okay, we're just showing exactly how this can be obtained under tests. Yeah, but hey, and the test conditions, some of these, this will be quite a very intense one in a test. So we start by 1/4. Right, we start with 1/4. All right, we start with 1/4, and then we have the sec. Okay, now that's very interesting. How do you do the sec on the calculator? It's 1/course. Right, so you're going to do 1/course, but now this one, because it's sectan, so the sec is 1/cosine, and this is sine of a cosine. Okay, so let's just do that. So we're going to do here 1/cosine of 1.107. Okay. And then you have the sine. Okay. Calculator is in radians. Just set it that way now. All right. So the sine is 1.107. And then we have the cosine, 1.107. Right. Okay. Then we have the lean. Lean is this one. And then we have the secant here. You need to make sure that our brackets are the correct number. Just wanted to do it at once. Okay, so you'd have the 1/4 and then the first one in brackets. And then the sign in its own brackets. Yeah, it's fine like that. Okay, let's see what we get. Then the lean. Okay, this lean then is going to be the sec. Yeah, but you can try this one and say 1 over the cosine. 1.107. Like that. Plus the tan. Plus the tan of 1.107. Remember, we're just doing the one denominator. Okay. And then close. Yeah. Let's see. So we're getting 1 point, because we're doing the one denominator. Okay, the integral from 0 to 1 of the 4y squared plus 1 dy. And the denominator, we can see that it is 1.479. Okay, obviously, because we rounded off the limit of integration, the 1.107 would have obtained, but doesn't really matter. It's only the, okay, because it's to a certain number of the decimal places, like 3 decimal places. So you can see that it is actually just the third decimal place that is affected by the rounding off. So, but you're able to see that it is 1.479. And this is how you would do the integration of the denominator. But there are tables that, there are integration tables that you can use. So and they save a lot of time. Because now sometimes you might not really do all these things in the exam. It's not very realistic, right? But now we would then say, by like the same token, by the same reasoning, the integral from 0 to 1 with the y squared, but I realize that the y squared is just going to have something extra here. It might turn out to be very simple. Let's just check. Because see, this one alone from these produced a sec cubed. Sec cubed. And then this one is y squared. It's going to have like the tangent squared, because we use the tangent, like y becomes y equals the tangent. And then here you can use that. You can use y equals 1/2 the tangent. But now it's going to have something extra. It's going to have higher powers. Sorry, it's going to involve a bit more like techniques of integration. But the answer then, obviously, for that one is 0.6063. And then if you divide this two, you get the 0.410 meters. Now, what about the y bar? It is the integral of the y tilde dl over L divided by integral of dl over L. You integrate from 0 to 1. Why from 0 to 1? Because we know that y is also from 0 to 1, as much as x is from 0 to 1. And this is a description of this particular rod that we're dealing with. And we have learned that this is the wire rod kind of analysis, because we have learned that the center of a line is studied using this dl, because it's a line dl. And now the example of this rod is like a thick wire kind of a situation. So right, we had to obviously to spend a bit more time on that. And I wanted to also just elaborate on the fact that there are more examples that we're going to do on this, but there are like tons of them. Like if you look at the integral of the integral of the y tilde dl over L, it's going to be exactly that. Why is it that? Because y tilde is y, and the dl, right, the dl is the square root, right? The dl is the square root of 4y squared plus 1 dy by using Pythagoras theorem for the wire. So that is why then we come here and we then say this one, the dl here, it's going to be the y tilde is y, and then the dl is the square root of the 4y squared plus 1 dy. The dl is still 4y squared plus 1 dy. Okay. Obviously, just a bit more calculations congested on this particular screen here. And then, now, what then we do? The denominator is the same thing. 1.479. It's only the numerator that's a little bit different. Okay, now we're going to explain this one. Right, so you're going to explain this one. Okay, this one is easy, but very easy. Okay, so all these integrals that are going to come there, you need to be just very careful in terms of the fact that they are cunning yet easy. They're cunning yet easy. They're cunning yet easy. So what do we do? What we then do is the following. So what we then do is the following. All right, look, I want to discuss this one. Okay, because this one is the same. What we're going to use the substitution. The substitution is 1/2. So you let y be 1/2 tan theta for the top one. And the answer is going to be 0.6063, like we did. But yeah, we're going to spend a bit more time on that. But I want to explain this one, because the top one, the bottom one is the same, 1.479. The integral of the square root of the 4y squared plus 1 dy from 0 to 1. What about the integral here from 0 to 1 of y, the square root? Okay, this one is easier. You can do it in 2 ways, because it has y here. So because of the y there, you can use u substitution. Right, so you can let u be 4y squared plus 1. du is 8y dy. So you have y, the integral of u. Yeah, right. What is dy? Is du over 8y. Y cancels. Okay, you can draw a small table like this. Normally I do. And then you have the y, which is from 0 to 1. And then you would have u. Right? When y is 0, you put here in the place of y, you put 0. 4 by 0 is 0. Plus 1 is 1. So u is going to be 1. Y is also 1 because integrating from 0 to 1. When y is 1, you put 1 in the place of y, you have 4 plus 1. 1 in the place of y is going to be 1 squared. 4 by 1 squared, which is 4 plus 1, giving us a 5. So the integration is going to be actually from 1 to 5. So we change the limits of integration. Right, exactly from 1 to 5. And then now this is y, and then now this is u. Okay, because then why do we use u here? And then here we use some tangents and secants and things. Because this one, we consider the derivative of what is under the square root of 4y squared is just 8y. So it produces a y term. Because it produces a y term, then it's easier for us to just let u be this. But here we can't do that. Because if you let u be this, then it's going to be like the derivative of the 4y squared plus 1 is like 8y. It has nothing to do with y squared. So, yeah. Now, here, if it's 8y, then here you make dy the subject. What is dy? The subject is du over 8y. So 8y cancels. And then we have 1 over 8, the integral of 1 out of 5. This cancels. So you have 1/2 du. And then now, which is 2 over 3 u to the 3 over 2, the integral of 1 to 5. Okay, you multiply by 2 here. 1 by 2 is 2. Yeah, we can simplify it. We can simplify it a little bit. How so? We can say, for example, here, 2 divides 8, giving us 4. 4 by 3 is 12. It's 1 over 12. Okay, then we have 5 to the power 3 out of 2 minus 1. Okay, then obviously this is the integral of this one, the integral from 0 to 1 of the one with the y. Which one? One with y. It's the top one. Now the top one, if you use the calculator, then you get 0.8484. Just try that, but yeah, it's good. That's what we're gonna get, because obviously this is correct answer. We're just trying to verify the working here. So let us verify this quickly. So then what we're going to do here is the following calculation. So we're going to do 1 out of 12. So you have 5. 3 divided by 2. All right, so, okay, it is 0.8484. 0.8484. So it confirms therefore that the integral of the top one, okay, the top one is easy because just using t substitution. Because why does the t substitution work? It works because if you let u to be what is under the square root sign, then it produces a y term, which is 8y. And therefore, because of that, then y is able to cancel. Y is able to cancel y, and therefore give us the 0.8484. Okay, so obviously now with this, then it is straightforward. Then if you look at the 0.84, okay, let me just do this here. So if you look at the fact that we have 0.8484, you divide by 1.479, okay, yeah, easy. It is 0.574, okay, to like 3 decimal digits. And so Now, this actually therefore becomes, what is this thing? What are these things we're getting? What are these things we're getting? Okay, these things we're getting are actual coordinates of the centroid. They are the centroid of a line, right? So in other words, the centroid of a line, which would be x bar, y bar, would be equal to, the x bar would be 0.410, and the y bar would be, so in meters there, the y bar would be 0.574 meters. This would be the actual coordinates of the centroid of this, of the rod. The coordinates of the centroid of the rod. In other words, this would give us the coordinates of the centroid of the rod. Okay, now you need to obviously think about this and make sure you sort of understand. I can give you a small homework. What is the homework? Okay, because the next one is different. Now the homework is that you need to refer to this example again, because I'm going to send you this recording in the next couple of minutes. Okay, it is going to take maybe like 30 minutes or 1 hour max, because it takes time to load because of the length, you know. But now, we'll send you this recording, right, in 1 hour maximum time for, after we finished. And then now you would consider this example: locate the centroid of the rod bent into the shape of a parabolic arc. And then now you come here, you use the differential element, you're able to get the DL, and then use the fact that it is given that y tilde is y and x tilde is x. Okay, so there are times when you're going to calculate it, right? There are times when you're going to calculate it. And in general, once again, there is y tilde, x tilde, which can be something else, for the general centroid of a line description. All right, so but now I want to mention something here. I want to give you the homework. What is the homework? The homework is easy. Right, the homework is, okay, this is obvious. There's nothing to do here because it's repetition, that the DL used Pythagoras theorem to get it. And the x tilde is x, y tilde is y. Okay, it's given the question. Then your homework is to verify, because we verified together the bottom, so you must verify the top. So you'll have to verify that this one here, this guy, is actually equal to what? Is actually equal to this. Is actually equal to 0.6063. It might take you the whole day to do this. So I'm going to share some integration tables in our next meeting. Integration tables so that you can like be able to cross-check your answers to save time. Okay, because some of these are very long, but so yeah, but most of the time they're going to be easy because they know very well that if it's going to be difficult, they might give you the formula there as part of the question to say hints, this integral is equal to this, something like that. Right, so but now I'm saying the integral from 0 to 1 of y squared, the square root of 4y squared plus 1 dy, is equal to 0.6. Let me be clean up here because you might not see very well. I don't want that. I don't want you to then say, okay, I couldn't see very well because we don't need the rest of this. I'm then saying you need to verify that this integral here, is what? This integral here is actually the same as this integral, the top one, from 0 to 1 of y squared, square root of 4y squared plus 1 dy. This integral is 0.6063. 0.6063. 0.6063. That is the integral of the top. And therefore, the result is 0.410 meters. Verify that the top one is, I think the homework is very clear. Verify that this integral is equal to this. But we shall continue tomorrow at 10 p.m. again. Any question?
No,
Okay.
thank you so much.
All right, let's find things. Once again, you just do that. And once again, to do that, you don't need to crack your skull and be like, where do I start? The substitution is let y be 1/2 tan theta, like we did. But it's going to be some integration by parts and some other things. But I want to see that you can be able to show that this is equal to 6.6063. Okay, it's going to take some good amount of effort, integration by parts in a couple of techniques. Yeah, but it'll be interesting to see that you can do it. Right, we thank you for joining us. We shall send the recording even tomorrow at 10 p.m. we're meeting. And there are like lots of problems we shall do. The past tests and past quizzes and like past exams. We have like lots of them for this module. So, right, we are building the momentum right now. We just have an idea of what's going on. But tomorrow we shall dive deep into like more problems. Okay, but we thank you for joining us today. Right, until tomorrow, take care. And we shall send you the recording in the next couple of minutes. But take care and good night. Okay. Thank you.